Hi, this is Prasanna from Viveknamia. In this video, we are going to discuss about how to simulate the boost converter in closed loop using Matlab. So straight away, we'll move on to the Matlab. So in this simulation, I'm going to use the combination of proportional plus integral plus derivative, that is PID controller in my closed loop. First, I will develop the boost converter and then we'll move to the closed loop. Okay. So for the development of boost converter, I need some components. I need a boost inductor, filter capacitor, load, switches, diode. First, I will select all the components. So in this series RLC branch, I'm going to select only the inductor. So from the next one, I'm going to select only the capacitor. From this, I'm going to select only the resistor. I need IGBT that will act as my switch. So in this IGBT, it's having the fourth terminal. Actually, collector, emitter, gate is there, and one more terminal M port is there. Actually here M port is not necessary in our simulation. I'm going to disable this M port. Now the switch is having three terminals: emitter, collector and gate. Fine. Similarly, if you take diode is also having a three terminals. M port is there. I don't want the M port. I'm disable this one. So now this diode is having anode and cathode terminal. For the development of this boost converter, you can refer my old videos also. We already did one more video regarding the development of boost converter in open loop. Okay, so in that video, I used a DC voltage source as a input voltage. That's a constant input. Okay, but in this simulation, I'm going to give the variable input. That will see how to do that. For that, I need a voltage measurement for the measurement of input voltage and output voltage. So first I will simulate the system with constant input in closed loop, and then we'll do the same closed loop simulation with variable input. If you want to measure the current through the inductor, you can go with the current measurement. Okay, fine. Now, so this is my system. Actually, I want to do it in closed loop. So I'll fix my set point. Say my set point is 30 voltage. Irrespective of variation in input, the output voltage across the load resistor will be 30 volts. So that's the intention of this simulation. How to do that is I have to compare this measured value with my set point with the help of a comparator. Yeah, just I'm changing the position for my simplicity. So now if you want to see the output, you can use the scope, no issues. Now the input voltage is compared with the output voltage. My intention is I want to compare my set point with the measured value. Here I am fixing some constant, that is my set point voltage. I can say that my set point voltage is 30 volts. Okay. Now the set point is given to the positive terminal and the measured voltage is given to the negative terminal. Okay. Now the output of this comparator is, this signal is nothing but it's a error signal. So this error signal is normally given to the PID controller. Values and all I will do it later. I will submit later. I'm flipping it. Now that error signal is given to the PID controller. You cannot straight away, actually the output of PID controller is a control signal. You cannot straight away given this um, control signal to the gate signal because it won't work. It won't work actually. Here we have to generate the pulses because I'm having a switch. Okay, if you want to make the switch on and off, the input must be in the form of pulses. Okay, how to generate the pulses is I need a repeating sequence. I have to compare that, say it is my carrier signal is a sawtooth. Okay, so I'm just doing some, I'm generating sawtooth carrier signal. Okay, here the values I'm giving is time value is 0 and 0.00004. Actually this is nothing but it's a switching frequency of carrier signal. Actually this value represents its the time period. If you want to know the frequency, f is equal to 1 divided by t. If you substitute this, you will get the switching frequency of this carrier signal. This carrier signal is nothing but it is a sawtooth wave. Okay, sorry. And output values, it should change from 0 to 1. So now the carrier signal is compared with the PID output. I'm taking a relational operator, I'm flipping it. So now when the carrier signal is less than or equal to the PID signal, at the time I'm instructing the circuit to generate the pulses. So now the pulse is generated accordingly. This is nothing but my input voltage, and this is nothing but I can say it's my inductor. And this one is diode. And this one is the load. Okay, and this is nothing but my PID controller, and this is comparator. Fine. So now I'll slowly give the values. I need a power guide. So first what I will do is I'm changing this power guide into discrete one. I'm changing this as 5 e power minus 7, and then go to modeling, go to model settings, let the solver type will be variable step as it is. I'm going to change the solver method. I'm going to use this ODE23T method, and then I'm changing the relative tolerance as 1 e power minus 5. Then only my system will work properly. And the algorithm I'm using is adaptive algorithm. Click OK, and then give some input voltage. Say it is 12 volts, so 12 or 15 volts, whatever it is, let it be 15 voltage. Okay, so you know that my set point is 30 volts, whereas the input is 15 volts. I can say that this is my set point or target or reference, whatever you can take it as. This one is set point, or you can say it is reference, whatever it is. Okay, this reference voltage is 30 volts, but the input voltage given is 15 volts. And inductor value I'm going to choose is 75 e power minus 6, 75 millifarad, sorry, 75 millihenry. And then the capacitor I'm going to use is 250 microfarad, 250 microfarad, and inductor is 75 microhenry. Okay, inductor value is 75 microhenry, whereas capacitor value is 250 microfarad, and the load resistor I'm going to use is 50 hertz. And then the repeating sequence I already mentioned. It's having the it's nothing but a sawtooth generator having the carrier frequency of 1 divided by 0.0004. Okay, and output values are 0 to 1. Here in PID controller you have to design the KP, KA, KD values. We are for calculating KP, KA, KD, please refer my old video. Okay, so in this PID controller I'm going to use discrete and PID, and then I'm fixing my proportional value as 0.45, integral value as 43.5, and derivative value as 0.003452 3425. Okay, so these are all my kp value, ki value and kd value. And go to output saturation. Here I have to fix my lower limit is zero point 0.1 and upper limit is zero point 0.9. Okay, apply it. Okay, now everything is fine. Now if you run the system, you will get the output. Of course, I will reduce the simulation time. Okay, so let it be 5 seconds. And go to scope. I'm changing the style. First one is, I'm fixing this as 2 and it is black. Actually the first one is input voltage, whereas the second one is output voltage. Okay, if you want you can add the legend. First one is input voltage. Okay, now if you run the system, it will work properly. So here, if you look at this, the black one is the input voltage, it's having a 15 volts, and the output voltage is blue one, it's giving the 30 volts exactly as per our requirement. So now the closed loop system is work fine. Suppose if you are giving a variable input, okay, so here whatever it is, the input is a constant input. If you give variable input, whether my system is working fine or not, let us check. I'm just deleting this DC voltage source. So here, I'll do some changes. I'm adding one more gain here. Okay, that I will do later. I'm going to give some variable input with the help of a component called signal builder. Okay, so signal builder which will help you to generate a different signal with respect to the time. If you double click it, you can come to know. You can go to signal, go to new. Actually, if you want to develop a constant step pulse, sawtooth, square, whatever you want, you can do it. Even you can generate noise also, but I'm not going to use this all the default one. I will design my own, I will develop my own signal. I'm going to custom. Okay, here you can refer the time values within the square braces. I can say that this is 1 5. Okay, so up 0 to 5 I'm going to generate the value of, say it is zero point 0.6. I'm giving some values 0.7. So this is 0.65, 0.65, and then again 0.75. I'm just doing some changes, that's all. So now if you click OK, you will get output like this. I'm deleting the previous one. Okay, now go to again access, go to change time. I need minimum time is 0 and maximum time I'm going to simulate only up to 6 seconds. Okay, click OK, save the signal. So this is my input signal. Okay, of course, if you look at this, the exact y value, it's having a 0.6, 0.65, 0.7, 0.75. Actually, I want my input value should be, it's a variable one within 8 volts to 15 volts. For an example, I'm telling. Okay, how to make this variation between 8 volts to 15 volts is, if you multiply all the amplitude value with the set point gain value, say it is that in multiply with 30, you will get the output voltage variation within 8 voltage to 15 voltage. Okay, that's what I'm going to do now. I'm saving this file, closing this one. Okay, so I'm going to multiply this signal with the gain block, and the value of gain is 30. That is nothing but my set point. So now this is given. Now the signal is, the variable input is generated. You cannot directly give this variable signal. So I need a controlled voltage source. This controlled voltage source actually, whenever the signal is given to the controlled voltage source, it will generate the equivalent voltage signal. Okay. So now that variable signal is given as an input to this S port, and you can take the output from positive to negative. So for some modification I'm doing here, in between the comparator and PD controller, I'm going to use a gain block. Say that just for manipulation purpose, I'm making this 1 divided by 30. Fine. So this is the closed loop simulation with the variable input. Let us see how actually the thing is working. I'm changing the stop time as 6. You don't need to change any values. That PD holds good for all the input variations. Now if you run the system, I'm just making my PID controller this derivative value as 0. Okay, as of now. Then, oh, stop time is 56. I don't want this only for 6 seconds. Yeah, that's a main. Now, if you run the system, it will work fine. So, at each and every second, at 1 second, I change the input variation. At 2 seconds, again, I change the input voltage. So, whatever the changes in input voltage, my output voltage is maintaining at a constant 30 volts. Always trying to maintain 30 volts because of its closed loop. If you look at this portion, it's a critical portion where the input is changes as a slope. Okay, it will act actually. It's a it's a changes with respect to time as a slope, and at that time also it's trying the my closed loop is trying to maintain as a constant output voltage. So in such a manner, this system will work effectively in closed loop system according to this Kp, Ki, and Kd values. Okay. So this is a way you can easily develop the closed loop boost converter simulation. Hope this video will be helpful to you. In upcoming videos, we will see how to develop the closed loop buck converter, buck boost converter, and so many things. Kindly watch the channel videos. Please subscribe the channels. Thank you.